Hello, my name is Daniel Nenny, and I'm the founder of SemiWiki.com, the open forum for semiconductor professionals. Since going online in 2011, SemiWiki.com has experienced more than 3 million users. If you're not a member of the SemiWiki community, please register as my guest. I hope to see you there. Today's webinar is titled Reduce Risk and Improve Quality of AMS IP Using AI-Powered Automated Timing Arc Prediction in partnership with Empyrean Software. The webinar will focus on a new AI-powered automated timing arc prediction and validation capability, which is the first commercial capability of its kind for standard cells, AMS IP, and memories. It automates an otherwise manual task and reduces the risk of delayed tape-out or multiple silicon iterations. Today's presenter is Anju Shea. Shea is a senior application engineer at Empyrean Software. He is responsible for customer support of design tools and methodologies for SoC design. Shea has extensive experience and expertise in tool automation and design methodology development. Shea received a PhD in electrical engineering from UCSD. Okay, let's get started. Over to you, Shea.
Dan, thank you for the introduction. Now, to audience, thank you and welcome to the webinar on automatic timing arc prediction for AMS IPs. I will put up each slide and let you read it for a few seconds, and then speak slowly so that you can understand my English, which has a strong Chinese accent. Having said that, the capability I am presenting today is new. NVIDIA, one customer of ours, presented a paper on their use of this tool at DAC 2019 in the designer track session. Let me get right into the presentation. Timing arcs for digital IPs are well under control, but that's not the case with AMS IPs. Predicting timing arcs for AMS circuits is also a manual process. It takes a team of designers to produce a comprehensive set of arcs for AMS IPs. That means it is time-consuming and risky. It is risky because it is manual and hence is error-prone and has a high potential for missing arcs. In today's world of safety-conscious SoCs, manual timing arc prediction is a liability. Process technology alone brings up a slew of the quality and the risk issues when an IP gets implemented in that technology. The issues are triggered by minimal geometries, thermal effects, variation, and more. Most of them end up impacting circuit timing for the IP. Under these conditions, manual timing arc prediction dramatically increases risk. In addition to process technology, it's common to see IPs being used in design applications and in markets that the IP designers never expected. Manual prediction of timing arc could eventually lead to problems like dead time to market or silicon failure. How can you trust, for example, an SoC implementing the autonomous driving function using one or more IPs with timing arc predicted manually? Timing arcs are critical elements of an IP model, and they must be generated automatically across all modes and conditions. Fortunately, AI and machine learning techniques have advanced enough to make that a reality. The fact that AMS IPs are evolutionary in nature, prior data is a huge asset for training and inference algorithms. Let's see how the AI-powered flow helps timing arc prediction and reduce risk. Apart from large amounts of data available, advances in software and hardware technologies have enabled the use of AI and machine learning for automatic timing arc prediction. Essentially, it involves a set of flows, starting with initial training, prediction, and incremental trainings. The incremental training, which takes use model, process, and other changes into consideration, drives for continuous improvement to the machine learning model. Let's look at the detailed flows. An initial training flow uses prior and current data, use models, and a range of weights to generate a machine learning model. The prediction flow uses that machine learning models to predict all the arcs. However, changes to use models and the process technology require the machine learning model and the resulting timing arcs to be updated. The incremental training flow drives the continuous improvement to the machine learning model to enable accurate and automatic prediction of a comprehensive set of timing arcs. Automating the timing arc prediction offers not only the most comprehensive set of the timing arcs for an IP, they are more accurate too. With machine learning technology, the number of false positives and negatives are reduced as well. Of course, the proof is always in the pudding. Let's see some actual results. Here is a real test case to highlight the effectiveness and the usefulness of this solution. Dataset with 411 IP blocks are used with existing timing arc database and 1.8 million arc sample for training. This training was applied to a test data set of 30 IP blocks with 15 million arc samples. It took 46 minutes to generate the machine learning model. After factoring in the result of the designer's review, the incremental training process took only 10 minutes to generate a refined machine learning model. The benefit of the incremental training flow and the refined machine learning model are clear from the increases in the number of predicted timing arcs from 84.3% to 99.6%, and the timing type from 83.6% to 98.9%. Here is the plot of the distribution of missing arcs by IP blocks. The accuracy of missing arc prediction through incremental training flow for all IP blocks improved by more than an order of magnitude. For example, FP count per IP blocks is fewer than 100. The only exceptions in the plot are those 3 new IP blocks, which anyway didn't contribute to the incremental training data. Summarizing, the automatic timing arc prediction is definitely an asset for AMS IPs, and even more so when those IPs go into today's advanced chips used in safety-sensitive applications like automotive. It all comes down to coverage, accuracy, and speed. NVIDIA presented a paper at 2019 DAC in the designer track session. The paper was titled Machine Learning-Based Timing Arc Prediction for AMS Design. It is now in their production flow. That is a great endorsement to this AI-based automatic timing arc prediction technology from Imperial. Thank you. Now it's time for some questions.
Thank you, Shay. All right, let's start the Q&A. First question. On our standard cells, we have neither had difficulty coming up with timing arcs nor encountered missing timing arcs. Hence, how real is this problem?
This tool is targeted at the AMS IP, which are much more complex than standard cells. It typically takes a team of designers and using a spreadsheet-based manual method to come up with the timing arc, which is very time-consuming and error-prone.
Okay. Another question. Training requires lots of data. How do you get the data for a new IP?
Almost always a new AMS IP is still a new incarnation of an existing set of IPs The tool extracts the training data set from timing models out of the previous project or prior version of timing model of the IP involved in the new IP.
Okay. Another question, does Qualib-AI need any special type of hardware platform to run AI algorithms?
The answer is no. It just runs on standard CPU platform.
Okay. Another question, would Imperium help in bringing existing AMS IP into the Qualib-AI flow with data migration?
Yes. If IP timing models are written in a format other than Synology's Liberty.
Okay. Does your system cover timing arc attributes like conditional arcs?
Currently, the tool supports the timing type prediction of timing arc attributes. As for supporting timing sense and the conditional arc attribute prediction are on our roadmap.
Okay. Another question, what is a confusion table?
A confusion table is a table that is often used to describe the performance of a classification model, or we call it kind of classifier, on a set of the test data for which the true values are known. It allows the visualization of the performance of a machine learning algorithm.
Okay. What if I don't have enough training data? Will you provide already trained model?
Yeah, this is a good question. Our incremental training flow allows users to start with the little training data and continuously improve its accuracy when the training database quality grows over time.
Okay. There's another question. Does it support multi-threading or GPU acceleration?
Currently, the tool supports parallel processing at the prediction stage, not yet at the training stage.
Okay. One last question. Is there a competitor's tool that does this?
We are not aware of any similar tool provided by other EDA vendors.
Okay, that's the end of our webinar. Thank you for attending and have a good day.